There, okay? Can you stick those over there? All right, so today, as you can see, we're going to talk about clustering. We hinted at this at the end of last lecture, that handling the problem of how we cluster unlabeled data is just really a special case of the problem we talked about last lecture of how we would use EM to learn a Bayes net when we only have some of the variables observed some of the time. And so clustering is just a special case of that, so we'll talk about that. And also we'll talk about learning the structure of Bayes nets. So moving right along. This is just to imprint this on our memory. I'm not even going to say it. Okay, so unsupervised clustering. The problem here is many people would describe the clustering problem with a picture kind of like this. It says, well, if I have some unlabeled data, maybe grouping people by a couple of features like, say, height and weight, then sometimes it's useful just when you're getting a look at data to try to find whether it clusters into different groups. And we can think of that problem as we can model that problem a couple different ways. When I first encountered the clustering problem myself, I thought, this is a silly problem. Silly problem for me to spend time on because there is no wrong answer. Right? If you give me a bunch of data points and you say, guess what the clusters are, okay. I'll draw a circle around some of the points. I'll say, that's a cluster. Here's another one. And you haven't really specified the problem well enough for me to know whether we should prefer the clusters that I made up or the ones that my friend Harry makes up. So in that sense, it's a silly, underspecified problem. But we can make it into a well-defined problem if we take the point of view of saying, well, we want to train some probabilistic model, a Bayes net, for example, to cluster these points. And we'll specifically say that the best clustering is the one that maximizes the likelihood of the data. So if you give me two probabilistic models that can cluster the data, now I have a basis for choosing between them. I'll prefer the one that assigns the greatest, that makes the data most probable. I'll prefer that over somebody else's clustering that for the same data points makes that data less probable. So, so I've mended my ways. I no longer think of clustering as a silly problem because I see this way of making it into a well-defined algorithmic question. How can we estimate the parameters or some Bayes net that allows us to cluster the points in a way that makes them most probable? And so that's the way we're going to proceed. And in general, when you look at the literature on clustering, you'll often see the phrase mixture distribution. And this is the kind of probability distribution that we try to use to model the data when we have clustering problems. And as you'll see, it's a very commonsensical thing to do. Suppose I have data points that are described by n features. So each data point has is described by n random variables. And a mixture distribution is just a particular kind of probability distribution, particular kind of joint probability distribution over these random variables that takes on this particular form. So we say the probability of any given data point with features x1 through xn is going to take this form. It's going to be the sum over the possible values of some latent variable, z, and this z really you can think of as the name of the cluster. Or actually, I guess I should say I is the name of the cluster. Z is the cluster variable. Right? So I'm going to have a latent variable z whose value, it's a discrete valued variable, z. And for any given data point, we can't observe z. That's one of the unobserved variables. But it's going to be the indicator variable that indicates which cluster this data point belongs to. And then we'll have some other probability distribution conditioned on z. Depending on which cluster you come from, there's some probability distribution that determines the probability of any joint assignment of x1 through xn, given that you happen to fall into cluster z, or whatever the value of that random variable is. Okay. So you can think of it as it's just this way of saying the probability of any given data point is the superposition or mixture of several different probability distributions, p of x1 through xn given z equals 1, given z equals 2, given z equals 3, whatever. And however many clusters we want to say we have, that'll be how many values we'll allow z to take on. And then, and some of those clusters may have more data points in them than others, and we'll let that be reflected in the probability of z taking on a particular value. More populated clusters will have a higher p of z. And so you can think of it as just another way to look at this is, you notice that's the form of an expected value, right? It's the sum over the possible values of a random variable of the probability that it takes on that times this other quantity. So you can also think of this, if you like, this is just the expected value over p of z of this. Okay, and so then actually when we talked about naive Bayes, this is the form of p of xy that we talked about really, where y, if you think of naive Bayes and think of y as being the variable z here, then we're saying, well, the probability of any given data point is the probability of the label y, now z, taking on a particular value, times the probability of all the x sub I features taking on their values, given the value of the label. Uh-huh.
So we can choose I based on some arbitrary characteristics, saying we want a certain number of clusters, say 3. Is there a way to optimize I, but also put it without a penalty? Because you can imagine as I approaches n, you would get it to be more and more overfitting the data. So is there a similar analogy to that?
Yeah, this is a very good question. So the question was, how do we know how many values z should be able to take on? 2, 3, 17? How do we choose? And in this lecture, we're just going to say, we make it up. This would be a good midterm question. The midterm question would be, how would you use cross-validation to determine the optimal value for z? That would be an excellent midterm question. So you could try z equals 1, z equals 2, z equals 17, z equals 94. Z equals the number of data points that I have that I'm clustering, so that every data point gets its own cluster. And obviously, should be obvious, the more clusters we allow, the more values of z we allow, the greater we're going to be able to make the training set data likelihood. But if we held out some data for cross-validation, we would see that, for example, if we used as many clusters as the word data points, so that every data point had its own cluster, that model would not assign very high probability to the held out data compared to some model that might use fewer clusters and assign a smaller probability to the training data but a higher probability to the test data. Okay, so you could use cross-validation as a way of choosing, essentially trying out different numbers of clusters and then checking the cross-validated test data probability under the best 2-cluster model, the best 3-cluster model, the best 4-cluster model, etc., and then picking the one that gives the highest probability to the test held out data. And that would be a very reasonable way of choosing the number of clusters. In fact, I have used that myself in the past. There's another approach which we're not going to talk about in this class, but which is also very nice and elegant in a way, which is to use what's called a hierarchical Bayes approach, or a and put a prior on the number of values that Z can take on. Probability distribution over the number of values Z can take on. And then solve for the posterior distribution on that given the observed data. So it's like a hierarchical Bayesian approach. You'll hear the phrase non-parametric approach used a lot too for training probabilistic models where we don't know in advance exactly how many clusters we have. But that's beyond what we're going to cover in this semester, so I don't want to go into the details on that. But you should be aware that that's around. Yes?
So would the value that you picked for Z for the number of clusters depend upon the number of folds in your cross-validation?
No. The value you would pick for the number of clusters should not be particularly sensitive to how you do the cross-validation, as long as you do it in a reputable way, right? You don't want it. For example, if you do a leave one out, that should work just fine.
In that case, you would need to train this too many times.
Well, then if you have n data points, you're going to have to train n models if you do a leave one out. That, as we'll see, it's actually not that expensive to do. And who cares if computers work all night? I don't. That's what they love it. They love working at night. So. All right. So mixture of Gaussians is simply a mixture distribution where we make where we say, okay, this thing is going to be a Gaussian. Okay, so each cluster will be modeled by some Gaussian distribution. Of course, it'll have its own mean and its own variance. That's what it means to be a different Gaussian distribution. Okay, so then mixture of Gaussians clustering, which is a very common approach, we assume each data point then is generated by one of several possible Gaussians, depending on which cluster we assign it to. And if we want to generate a random sample, a random data point according to a particular mixture distribution, then we can do that by randomly choosing a Gaussian according to P of Z. That'll give us a value for Zi. And then, given that we've chosen that Z, then we go to that cluster. We pull out the definition of that Gaussian. It'll have a particular mu and a particular sigma. And then we can generate a data point according to that Gaussian. Okay. So it's actually very straightforward. But you see what we've done here is we've turned the question of how do we cluster data we've translated that question into the question, how can we estimate the parameters of this mixture probability distribution? And then if we estimate those, we'll have essentially defined each cluster in terms of a Gaussian distribution. And then, of course, we could assign any data point to one of those clusters probabilistically just by looking by using Bayes' rule and by looking at which Gaussian is more probable, would assign it the greatest probability. Okay, so let's, so to tie this back into the naive Bayes EM question that we were looking at last time, you see if I simplify this just by one little bit by making the naive Bayes conditional independence assumption, then I can train a mixture of Gaussian model that is really identical to the probability, the parametric form of the probability distribution that we trained for our Gaussian naive Bayes. And now, instead of calling the label Y, I'm calling it Z, because that's going to be the name of the cluster. And this just translates into the question we were talking about in the previous lecture. How would we train a naive Bayes classifier if we don't get to see all the labels on all the data? And now I'm just going extreme on that, and I'm saying, what if we get to see none of the labels? But I still have this kind of assumption that there's a mixture of Gaussians that generated the data. It's just that I don't have any of the labels on what any of those Gaussians were for any particular data point. Okay. So now we can just apply our same EM procedure we talked about last time. So to be precise about my assumptions here, I'm making the naive Bayes assumption of conditional independence of the xi's given z. For the sake of simplifying the arithmetic, let's assume we only have two clusters, and we know that in advance. So z can either be 0 or 1. And therefore, we're going to have to train, when we train this mixture of Gaussians model, same as when we train our Gaussian naive Bayes model, we're going to have to estimate a distinct mu for each value z can take on. That's this one. And for each x sub I feature that we have. And again, to simplify life, we'll assume the sigmas are all the same and that we even know them in advance just to make the derivation of EM easy. Although if you don't make that assumption and you have more time, you can derive an EM procedure in the more general case. Okay, so now the parameters of this Bayes net that I don't know are essentially the conditional probability tables associated with each of these variables. And what's this one? Well, this is, we'll call this pi. These are the probabilities that z will take on each of its possible values. And then here we have a mu for each of the possible z values. And for variable 1, here we have a mu for each of the possible z values in variable 2, and so forth. Okay, so to derive an EM procedure, to learn this Bayes net, assuming we believe this is the graph structure, we now have to apply EM to estimate these unknown parameters in the Bayes net conditional probability distributions. Okay. So when we do that, we get a very nice simple EM procedure that looks as simple as the one we talked about last time. That is, we're going to start with our data points. We can only observe the vector of x sub i's for every data point. We can't observe their z. That's the cluster label. We don't know it. And so on each E step, we're going to calculate the probability distribution over possible clusters for data point n, for each of the data points. So we'll just calculate the probability that this particular data point belongs to cluster 1 or cluster 0. And then during the M step, we'll update our theta in this case being all those mu's with all the subscripts and the priors on z. given that we've got these expectations that we calculated in the E step. Okay, so here's the arithmetic for deriving that rule. It's exactly the same style that we went through last lecture, so I won't go through it in great detail. But again, think about what we're trying to do. We're trying to train a Bayes net with partly observed data. So what we're going to do is, oh yeah, we can't use maximum likelihood estimates because we can't observe all the variables. So instead we're going to use the expected value of the full log likelihood. When I say full, I mean the probability of our observed variables x plus our unobserved variable z. And so to derive the EM procedure, what I need to do is derive the E step by figuring out how can I estimate for every data point in my training set the probability distribution on that z, unobserved z variable for that data point. That's the E step. And then on the M step, how can I update theta to maximize the expected full data log data likelihood. So here is in fact the E step and the M step, but well, okay, let's look at it. Here's the E step. And now what I'm asking is, how do we for every data point, given our current estimates of theta, get a probability on z? You know how to do that. It's exactly what you do when you apply your trained naive Bayes classifier to give me the probability for any new test example of whether y equals 1 or y equals 0. It's exactly the same question. It's isomorphic. And so here's the arithmetic for doing that, right? We're going to get the probability that z takes on the value k for the nth training example, given that the vector of x sub I values is x of n. Well, that's just the same expression we used in naive Bayes when we apply naive Bayes to predict the label for a new example. And if I substitute, instead of p of x given z equals k, if I say, well, that's a normal distribution based on the mu for zk and x sub I, then I just can rewrite it this way. And now I've written, this is just the same as the first expression, except that I've written it in terms of the actual parameters that are in that conditional probability, collection of conditional probability tables in the Bayes net. Okay, so this is just apply your naive Bayes classifier to get the probability of, on the nth example, of z taking on value k given the observed features of the nth example. Okay. And now when we do the M step, this is where it gets interesting. Of course, in the M step, what we want to do is we want to update our parameters to maximize the expected log likelihood. Well, I guess I should underline this thing up here. The expected full log likelihood. And again, when I say full, I mean both for the observed and for the unobserved. And let's consider just first the pi. That's the prior, that's our estimate of the prior for z equals 1. Okay, so to do that, first thing I can do is I can notice that the expected value of this thing by the chain rule is just, the log of that thing is just this. That's just the chain rule, right? The probability of x and z is the probability of x given z times the probability of z. If we're doing logs, it's the sum of their logs. And now notice pi, which I'm trying to optimize here, trying to take the argmax with respect to pi, pi doesn't actually influence this first term. It only, pi is just the probability that z equals 1, so it only influences this second term. And so I can write out that second term this way, and this is the same notation we used when we did the coin flip MLEs and MAP estimates before. Notice if z is going to either be 1 or 0, if it's, so this exponent is just the sum of the number of times z ends up being 1 and the number of times it ends up being 0. And so the probability of the data is just whatever pi is, raised to the number of times that z ends up being 1, plus 1 minus that raised to the number of times it ends up being 0. And then we can just carry out the arithmetic analogous to what we did really in the derivation of the maximum likelihood estimate for a coin flip parameter. And what's interesting about that is actually maybe this line. And here you see what's happening. If you remember the coin flip expression that looked like this, here we had something like the count, the number of times z was 1. And now that's replaced by the expected number, the sum of the expected values of z. So now we're essentially, instead of saying z equals 1 or z equals 0, we're saying there's some probability that z equals 1 for any given example, and we're summing up all those probabilities. That's the sum of the expected values of z. And here we're essentially summing up the probability mass associated with z being 0. So what used to be a count is now just the mass of probability assigned to z being 1 or 0. And now when we want to optimize that, we of course take the derivative of this expected log likelihood with respect to the parameter we're trying to optimize. And that gives us an expression like this. So now pi, again, the probability that z will be cluster 1, is simply the sum over all n data points of the expected value of z. The expected value of z is just the sum of the probabilities that z was 1 on each of those examples, normalized by the number of points. So again, this is the probability mass that we've assigned to z being 1 over all the data points divided by the number of data points. Whereas recall our old MLE estimate for a coin flip looked like this, except here we just had the count, the number of times it turned out being 1, instead of the probability mass that was associated with z equals 1. So a very intuitive result, although the derivation is a little bit full of symbols. Okay, and similarly we can derive the m step for the mu's as well. And again, it turns out we only have to consider one of the two terms in the chain rule expansion. And when we do, to make a long story short, we get this. And to understand that, let's compare it to what we would get if we had fully observed data. If I said, here's a set of data points, these ones have y equals 1, these have y equals 0. Tell me the mean for feature I when for y equals j, in our case we're calling yz, then you would just say, well, it's the sample mean of all those data points that for which y equals 1. And this would be the sample mean. It's the sum over all the data points of this indicator function, 1 or 0, depending on whether z takes on the value j, times the actual value of the feature, normalized by the number of data points for which z does take on the value j, just the sample mean. But now, again, that's been replaced by something more general in our EM version, because now all these delta functions that say 1 or 0, does the value z take on, does z take on the value j or not? Now they're just the probability that z takes on the value j. Okay, so again, this the nice thing is this m-step update just becomes kind of the soft version of our old MLE estimates. And that's not because we thought it would be a nice idea to just do it that way. That's because if we go back to basics and say, we want a rule that will give us the parameter estimates that maximize the expected log full data likelihood, then we derive what that would be, we get this. So it's not some heuristic that we made up. It's actually what you must do if you want to maximize the log full data likelihood. So it's very nice. Okay, so putting it all together then, here's an algorithm. You can implement it. It's very simple, even though the derivation of it was a little bit elaborate. The algorithm itself is very simple to implement. If you want to write a mixture of Gaussian clustering algorithm, here you go. Get your data points. In the E step, you're going to estimate all of the, for the nth training example, for all training examples, these probabilities of the point belonging to one cluster or another. And then on the M step, you're going to update the probability of Z taking on value 1 versus 0, and the mu's for each of those Gaussians. Just repeat that. Okay. And really, the only difference between this and what we talked about last lecture is, I think there we were talking about discrete valued x sub i's. And here we're assuming we have real valued x sub i's. So we have Gaussians instead of Bernoulli probabilities for those others. All right. So in a way, this was review of naive Bayes and also pointing out that it generalizes if we use EM with the same model as naive Bayes, same probability model. If we use EM instead, then we get this clustering algorithm. Okay, so now we're going to try and see if we can run this somewhat temperamental applet that I found, but which I like. And if we can, then it's kind of illuminating. Okay, so here we have, do it this way. Okay, so I'm going to clear everything here and make up some random points. Okay, so here are some random points. We only have two features now, x sub 1 and, well, they're called y and x here, but in our notation, this would be like x sub 1 and x sub 2. These are just points. We want to cluster them. And at this time, I'm saying there are two clusters. So the cluster can be cluster number 0 or cluster number 1. Pardon me?
I mean, there's another scroll bar inside, so...
Yeah, I'm trying to get as much of this on the screen. When I said temperamental, this is part of what I meant. So there we are. Those are the two features and the points. It doesn't work. I tried that. If you do this, it doesn't really change much. We could do that. But it doesn't give us the full thing. Okay, so here are our points. And what we see here are the initial random made-up values for mu and sigma for the two clusters. This is the starting point of our EM. And now we can run EM one step at a time. Oh, no, I guess we can't. We can run it normal, fast, or slow. So let's run it normal. And now you see those Gaussians, whoops, converged already. Okay, so let me stop that. Start over. Random points. You don't like those random points? We can make up some different random points. Okay. here are two initial, just made up values for mu and sigma for the Gaussian. We have two clusters, and I can run again. And now you see the steps of EM, redefining the mu's and sigmas for the two clusters. Okay. And there it is, converged. Okay, now, some of those points don't have as high probability as they would if we used more clusters. But you see what's going on. It's trying to, and you also see it doesn't take that many iterations for EM to converge in this kind of a data set. So let's try it one more time. I'll stop this, clear the points, make up some random points, and then run. Okay, so it's converged. Now, if you play with this applet, it's kind of nice because they let you change the number of clusters. Let's say if we use 4 instead of 2. And make up some random points. Now you see 4 random. I want more points. There we go. So you see 4 random initializations of the 4 Gaussians. And if I run that, okay, it's pretty reasonable. So you see what it's done. You can see very vividly what's going on in each one of those EM iterations. On the E step, the algorithm is re-estimating for every one of those data points whether Z equals 1, 2, 3, or 4, which of the 4 clusters that data point belongs to, with what probability. It's not it's not an all or nothing thing. This data point probably belongs to this cluster, but with some probability it was generated by one of those other 3. So there's a probability distribution over the possible values of Z for each point. That's the E step. Then on the M step, the mu's and the sigmas for each of the Gaussians are recalculated using those expected values of class membership of each data point into the respective 4 classes. Okay. So there's the idea. So there's our second, third example of EM. We talked about a few last time. But this is the special case of EM where it's essentially a clustering problem that we can solve by saying we're going to train a probabilistic model, a Bayes net, where we assume that the probability distribution over all the points is best modeled as a mixture of multiple probability distributions, and there's a latent, unobserved variable that goes along with each data point indicating which of those mixture components, which of the Gaussians it came from. Yes?
In this case, will it always converge to the same point given your starting assumptions?
Good question. Will it always converge to the same thing? No, it won't. So in general, EM is only... Okay, so let me say it this way. In general, EM is only guaranteed to converge to a local maximum. And I can't say with certainty whether mixture of Gaussians is a special case where there's only one local maximum.
No, it isn't.
It's not? Okay.
Actually, the global maximum is like infinity if you have one of these components explaining only one point, so it will have infinite likelihood there.
Well, the highest likelihood you can have is 1. You can't have a probability of greater than 1.
If you have like a component centered at one of the data points with zero sigma. That's
Right, that would make probability 1, not
that will
infinite.
go up, but
Well,
it doesn't do that.
It would be probability 1. I mean, you can make mathematical tricks by making 0 sigma Gaussians, but that's not the interesting thing. this is in fact a local maximum likelihood, local maximum expected full data likelihood solution. And I don't know whether mixture of Gaussians has the property that the local maximum is also the global. Okay, so I'm glad to see this applet worked, and I encourage you to play with it, therefore. I put the little instructions. It's actually in the middle of a JavaScript thing, so there's not a direct URL you can go to get where I went. You have to go to some other URL and then point at JavaScript things to get here. But I put on the slide the instructions of how to navigate there if you're interested. Okay, so that is what I wanted to say about EM, about mixture of Gaussians, about clustering. And here's really the punchline for EM. It's our way of upgrading our idea about how to do learning to handle cases where we can't observe every variable in every training example. The key change we had to make, whoops, I see. The key change we had to make was to give up on maximum likelihood estimates and instead make this expected value version of likelihood that we're going to optimize. And then from there, it was fairly straightforward. So we can use EM for training Bayes nets. That's very common. So far, we talked about maximum likelihood version of EM. But of course, this would be another, now this would be too, this would not be a fair midterm question, but we can talk about it. You could derive a map version of EM instead of an MLE version of EM, right? Instead of maximizing the data likelihood, you might instead say, no, I want to maximize that, right? Which of course is proportional to, or this thing is proportional to P of xc theta. Did I get that right? No. You should have corrected me, right? So, so just like before, we could have maximum likelihood criteria to try to get our parameters, or maximum a posteriori probability estimates, which required that we bring in some prior distribution on theta. We talked about Dirichlet distributions, beta distributions. We could use the same kind of machinery and change our objective from maximizing the expected likelihood of the data to maximizing the expected posterior distribution on theta. So that can be done too, although we didn't cover it in this class. But the thing that is kind of nice, and the reason I took us through those several derivations of EM and pointed out their close analogy to our former MLE and MAP derivations, is that you're actually in a position now that if you make up your own idea of how you want to represent some P of y given x or some P of x comma y, you're in a position where you could derive your own EM algorithm for training that model with partly labeled data. Okay. All right, so end of EM. Any final parting comments, questions, suggestions about EM? Okay. A very pretty thing. Okay, another and the final topic we're going to talk about in terms of learning Bayes nets. So we said before that you can think of Bayes net learning problems as lying in a 2x2 grid. We could have fully observed data or only partly observed data. If we have partly observed, we need EM. We could have a graph structure that's known in advance That's the only thing we've talked about so far. Or we could have a situation where we know the variables, but we don't know the graph structure or the conditional probability tables of the BaseNet. And of course, that's a more challenging problem because we have to learn the graph structure. And let's spend some time, let's just spend a moment looking at that. So in the general case, it is very difficult. If you don't constrain the graph structure in some way, it becomes a computationally intensive problem to learn the graph structure. But you know, I want to go backward. I don't want you to look at that. Before we talk about any of this how stuff, let's talk about what. Suppose I ask you to judge. I give you a data set, and I have two algorithms that make up graph structures for the BaseNet for that. And your job is, you don't have to derive the algorithms. You just have to look at two proposed graph structures and the data and tell me, do you prefer graph structure A or graph structure B? Okay. So every time in machine learning, before we talk about what is the algorithm, it's almost always the case that you should start by saying, forget about the algorithm. I just want to know the criterion that I'm trying to optimize. I just want to know how I would judge whether solution A or solution B is better. Once I have that criterion firmly in mind, I can usually derive an algorithm for doing it. Okay, so a question for you. I give you two different graph structures for a BaseNet. I give you the data, a sample of training data. What's the criterion by which you decide if you like graph structure A better than B? Sorry? Fewest numbers of nodes and arcs. Okay, there is a proposal. Others? BIC, okay. A criterion that we haven't yet talked about, but that's a good one.
Which assigns a larger probability of the data set.
Right. Which one assigns higher probability to the data? And I like that one, especially if I get to do the cross-validation version of that, right? So if I get to say, hey, I'm the judge, you're giving me the two graphs. Before you run your algorithm, just give me a third of the data. Okay, now run your algorithm on the other 2/3 of the data. And now you give me your two graphs. What I'm going to do is I'm just going to apply them to see what's the probability, the data likelihood, for the test set data that I held out from you. And whichever graph, I'll have to learn the CPT. I'll have to learn the conditional probability distributions that go with each graph. But we know how to do that. We've already talked about that. So I'll take your two graphs, I'll learn the parameters of those graphs, and I'll see which of those graphs assigns higher likelihood to the test set that I held out from you while you were running your algorithm to make up the graphs. Right? Same way you choose between two decision trees or two naive Bayes classifiers or two anything. Which one actually works better on a separate withheld set of test data? Okay, so that's what we'd like. We'd like the one that does the best, makes the best future predictions. Okay, so now doing that, finding that graph, can be complex if I just say, here are n nodes. There are a lot of graphs you can make up among n nodes. Searching around in that space is expensive and subject to overfitting kind of issues. And so what I want to do just to touch on this point, and again, keep in mind there's a whole semester-long course on Bayes nets. We're finishing our coverage of Bayes nets today. I just want to touch on one nice idea that has come out of research on how to learn Bayes net structures from data. And that is this. If we restrict the structure of the graph to be a tree, then it turns out there's a very nice and computationally efficient algorithm for learning the best tree-structured BayesNet for any set of data. And first of all, what do I mean by a tree-structured network? Of course, a BayesNet is always a DAG. It's always a directed acyclic graph. But it's not always necessarily a tree. There's a DAG. That's a directed acyclic graph. All the edges are directed. There are no directed cycles. But obviously, that's not a tree. Okay, so if I restrict the graphs that I consider to be only trees, put another way, every node has only one immediate parent, at most one immediate parent. Okay, if I make that restriction, and you can think about what the corresponding restriction is on how the joint distribution is factored into subterms. But if I make that restriction, then there's a very nice, simple, easy to understand, easy to implement, well-justified algorithm that guaranteeably finds the best tree-structured BayesNet graph for any set of data. Okay, and first of all, what do we mean by best? Well, I'm going to say the best graph structure is the one that maximizes the Kullback-Leibler divergence, the KL divergence, between the distribution that I get when I use my tree-structured, T for tree, structured network, and the actual unknown true joint distribution on the variables in my BayesNet. Okay. So I'm going to use this bold X to indicate the vector of all the variables in the BayesNet. So if I have a BayesNet with n variables, x of 1 through x of n, then bold X means the whole collection of variables in the BayesNet. And so P of bold X is just the joint distribution over those variables. I don't know it. All I have is a sample of data from it. But what I would like to have is the tree graph such that once I learn the conditional probability tables for that, and I have the joint distribution according to that BayesNet, I want to make the KL divergence between the true joint distribution, even though it's unknown, and the one that I can get from my tree graph as small as possible. The KL divergence you recall from an earlier homework assignment, and you're probably asking yourself at that time, why are they making us derive these relationships between mutual information and entropy and KL divergence? We're about to see. But KL divergence, you'll recall, is simply the sum over, again, X is the vector of all the variables in the network. So this is the sum over all possible joint assignments of all the variables in the network of the log ratio of the correct probability to the probability assigned by our BayesNet. The expected value of this log ratio. Okay. And of course, if our tree nails it, if the tree actually learns P of X correctly, this ratio will be 1, the log of that will be 0, the distance will be 0. Okay, otherwise it'll be positive. Okay, so what we're going to be able to, what we get with the Chow-Liu algorithm is an algorithm which takes as input a set of variables and a collection of data, and then it returns the tree structure that minimizes the KL divergence with the true joint distribution. Okay. So now, how does this work and why? The way it works is amazingly simple. The way it works is based on this key theoretical result. The theoretical result says if you want to minimize the KL divergence between the correct distribution P and the one given by our graphical model T, then it suffices to find the tree network that maximizes the sum where there's an edge. If we add up for each edge the mutual information between the two variables the edge connects, and then we sum all the mutual informations for each of the edges in the tree, what we want is we want the tree that maximizes the sum of those mutual informations. Sum over all edges in the tree of the mutual information associated with that edge. Maximizing that turns out, for tree structured networks, to be equivalent to minimizing the KL divergence between the true distribution and the one that we can represent with the tree. So mutual information, you remember, we've talked about that as early as decision tree lecture, and you've seen it several times since. And here's the key. The reason we can substitute this sum of mutual informations and maximizing that, the reason we can substitute that for minimizing the KL divergence is because of this very nice result that says the KL divergence, which again is defined this way, is also equal to, for a tree structured network, the sum over every node of the mutual information between that node and its parent. Of course, in a tree, you only have one parent. And if we sum over all the nodes, we're also going to sum over all the edges, because every node will have at most one edge, plus the sum over all the nodes of their entropy, minus the joint entropy. And these are the true entropies under P and the joint entropy under P. Okay, so now if we want to minimize this, therefore we want to minimize this quantity, we want to choose which edges to add. The great thing to notice is edges have no influence on what this term is going to be. That's just the entropy of individual variables. They also have no influence on what this term is going to be. So the only thing the edges influence are which edges we end up summing over here. And so minimizing the KL divergence equals minimizing this term, which, if I remove the minus sign, means maximizing the sum of the mutual informations over every edge in the tree. Okay? So this is very nice. What it means in one sentence is we can learn, if we have an algorithm that can find the tree with the maximum sum of mutual information along its edges, then we have an algorithm that will give us, out of all possible trees we could define over these random variables, it'll give us the best one, best meaning the one which has the smallest distance, the KL distance, from the true distribution. Okay. And so here's the algorithm. It's called the Chow-Liu algorithm. I give you a set of data and a collection of random variables, and joint, each row in my data set is a joint assignment to those random variables. Let's assume fully observed data. Then number one, oh, I see there are two steps one here. The first step one, you estimate from the data just these terms, the marginals on every variable, and for every pair of variables, the joint probability of those two, the distributions on those. Then in the second step, number one, you compute all the mutual informations for every pair of variables. In step two, we calculate the maximum spanning tree over that graph. So basically, in the second step one, when you're done with that, you have a fully connected graph between all the nodes in the tree. Now we just want to find a maximum spanning tree. Maximum spanning tree means a tree that's embedded in that full graph that maximizes the edge weights. Then, of course, that's an undirected tree. We add our arrows any way we like, as long as it forms a tree. No arrows pointing at each other. There will be many ways we can assign edge. There could be multiple ways to assign edges, but we do it in a way that gives us a tree. And then we learn the conditional probability distributions for that tree, and we're done. So it's very nice. So let's look at how that works. So here's a set of random variables with the mutual informations between each pair written down. So this is our almost completely connected graph. There are a few missing here to make it easier to look at. What's that?
Why does it happen that all the ways are 1 or something?
To make it easy to look at. We just made up these numbers to make it easy to look at.
I mean, do they mean like 1 divided by 5, 1 divided by 6?
Yes, yes. 1 over 5 means 1/5. Right. Okay, so this is an illustrative example. So these are different random variables and with edges that represent the mutual information between those random variables. And now we just want to look at how we find the maximum spanning tree of that. This is something you can do in actually n log n steps where n is the number of nodes in the tree. But here's the simple way. This one's n squared. First, we just decide we're going to include the edge that has the greatest mutual information. So 1 over 5 is the largest. Let's make that a green edge. That's going to be in our tree. Okay? Now we greedily pick the next highest mutual information. So it's a greedy algorithm. Here's another 1/5. So we add that one. What's the next one? I see a 1/6 down here. So we'll add that. Keep going. Here's a 1/7. But now something interesting. We've now coming out of node A, we've got 2 edges, and we now don't want to consider anymore the edge between B and D, because if we add that, it won't be a tree. So as we go, we make some edges, we remove some edges. I'm marking them red here so that they don't get considered. And then subject to that removal of edges that would make it a non-tree, we add greedily the next highest mutual information edge that, if added, will still make this thing a tree. And so that's it. Just keep going like that. So we add the edge from B to E, and that now rules out several more edges, which we mark red. And that's it. So there we are. So there's the spanning tree, greedily computed, but this is the maximum spanning tree. And as you see, it's undirected. So now as our final step, we have to make this into a DAG, directed acyclic graph. But that's pretty easy. There are several ways of doing that, one of which is this. Voila. So there's a DAG we can use. And this DAG has the property that of all the trees we could have defined over that set of variables, this one, once we learn the conditional probability tables that go with that graphical model, this one will have the minimum KL divergence from the true joint distribution, or the empirical distribution represented in the data that we have. Okay. So this is a very nice result, and I wanted to show you this because it is actually a practically useful thing. And it's also kind of elegant, and also ties together some of these properties we've been looking at through the semester. Mutual information, KL divergence. You know, we've looked at several statistical measures about how to quantify the dependency between different variables. And here there's just this very nice theoretical result that says we can use mutual information with a greedy algorithm here to find the best, in terms of KL divergence from the empirical joint distribution, the best graphical model tree graph. And then a simple algorithm for doing that that's very tractable. Okay, so in general, the problem of learning graph structures is much more complicated. It's rife with overfitting problems. there are all kinds of recommended heuristics for dealing with growing graph structures that are not trees. For example, some of them say, first grow a tree, and now add more edges or subtract some edges and so forth. But it's a big research area, and we're not going to go into great detail. One kind of interesting piece of work I just mentioned, to tie again together a couple of things we've discussed. It's a very nice paper by a guy named Nir Friedman from about 10 years ago now. He did his PhD thesis on EM approaches to learning graphical model structure and parameters. Very bright guy. And one nice chapter in that thesis, which is also a journal article in the Machine Learning Journal, talked about the following thing. He considered the question, well, we like naive Bayes, but it makes way too many independence assumptions, conditional independence assumptions. And so he said, what if we consider graphical models where the graph structure is not just naive Bayes, not just naive Bayes, but what if we also allow a small number of dependencies among the X sub i's? And in particular, what he did was he took this Chow-Liu result and he said, well, I can derive a nice algorithm that allows me to add dependencies among the X sub i's so long as those dependencies themselves form a tree. Right? Like what I've drawn there. I added an ingoing edge to each node, each one of our X sub i's. So each node has only one parent. That's a tree that I added inside the dotted box. And so what he did was he used the Chow-Liu algorithm, ignoring the variable y, and just among the X sub i's in our naive Bayes classifier, and showed that it's a very efficient, tractable, not hard to compute weakening of the assumptions of naive Bayes that can be automatically, where the tree among the X sub I can be automatically derived from the data and added. And therefore, it ends up weakening the conditional independence assumptions that we made with naive Bayes and giving us a more elaborate graphical model. But again, one which is very easily trained if we have fully observed data, the way we assumed we did when we first talked about naive Bayes. In fact, if we have only partially labeled data, you could derive an EM algorithm now for training the graphical model that I just wrote there, assuming that only the y variables are missing. It wouldn't even be hard. And also, you could derive the answer to the question, how would I assign for a new test example where I observe X sub 1 through X sub 4? How would you assign the probability that y equals 1 versus 0? You could do that too, right? So, so I like that paper by Nir Friedman because I thought it was kind of elegant and it talked about a very tractable extension to naive Bayes. But I wanted to bring it up here again to kind of point to an example of what you are now fully prepared to do, right? So if we had a take-home midterm, I could have asked this question because you would have had time in to work on it. I could have asked the question, given this graphical model, which has a tree among the X sub i's, number one, how would you use EM to train the parameters of that graphical model? Number two, how would you label new X sub 1 through X sub 4 instances by assigning the probability of y equals 1 or 0? And and you'd be able to do that. I'm not going to ask it on the midterm because in an 80-minute midterm, you're not going to have time to work out all those details. But really, you know what you need to know to do this now. So the BaseNet story is much longer than this, but not in this course. So we're going to end here our discussion of BaseNets. As you see, it's actually kind of a very central set of concepts for the course. It ties together some algorithms we've talked about before, and it's going to be the basis for several algorithms we're going to talk about going forward. Things like time series models, we'll talk about hidden Markov models, which, as we hinted before, are just another special case of BaseNets. But in terms of what you should know, you should understand the representation of these things, how they represent joint distributions, how we use d-separation to decode the conditional independence assumptions. You should understand a little bit about inference. Inference simply means, given a BaseNet which defines the joint distribution, how can I calculate any other conditional probability or marginal probability that I'm interested in. And you should know that, of course, if you don't worry about tractability, the default procedure is just to, whatever term I give you, like the probability of A given B, just go back to basics and find all the rows in the joint distribution for which B is true, and then look at the fraction for which A is true. But you should also know that that explodes when we have many variables, thousands of variables, then we have too many rows, an exponential number of rows in the table with respect to the number of variables. And so you should also know that there are some special cases where you can work out the probabilities just by looking at the graph structure, manipulating the terms. We did several of those in class. You should know that more generally, you can also use Monte Carlo methods and sample the joint distribution and then just count the fraction of things that occur in your sample. And then for learning, you should know instantly how to train Bayes nets if I give you the graph structure and the data is all the variables are fully observed in the training data. That's trivial. That's just going back to our old maximum likelihood estimates. If a node is discrete valued, then I just estimate the multinomial parameters. If I want to do a map estimate, I use a Dirichlet prior on top of that. If they're continuous variables, I might use a Gaussian distribution. Again, I could put map estimates if I put some priors on that. I guess we didn't really talk about very much about we didn't really talk about map estimates for Gaussians. But the principle you know. And then if the data is not fully observable, you know you can use EM. If the graph structure is not known in advance, then you should understand the Chow-Liu algorithm at least as something we can do if we're willing to restrict the graphs to just trees. But also in that Chow-Liu algorithm, you should see that that algorithm is very suggestive of what you might do in a more general case, because that algorithm is essentially based on the idea that mutual information, our old friend mutual information, is a good way of measuring the dependency between two random variables. And even greedy algorithms that add edges to the graph based on that statistical measure of dependency can be quite useful. So there's kind of the summary of Bayes nets. Just for completeness, I should say there are entire chunks of the field of graphical models that we haven't even mentioned in this set of 3 or 4 lectures on the topic. For example, if you look at the literature, you'll see quite a bit of work on what people call undirected graphical models. So we've looked at directed acyclic graphs. Some people prefer to work with graphical models where they're just undirected edges in the graph. Again, the nodes represent variables, and the edges represent the fact that these two variables are interdependent. But now the rules of the game of how we define a joint distribution over the variables, given that graph and accompanying parameters, the rules are different if it's an undirected graph. It's just a different notation for representing joint distributions. You'll see sometimes people talk about factor graphs. But all three of these things, factor graphs, DAGs, base nets that we're using, and undirected graphs, what they share in common is this, that the fundamental problem they're trying to overcome is that the joint distribution among a collection of n variables can be a very hairy thing to represent and a very difficult thing to learn if we don't make assumptions. And so conditional independence is the kind of assumption that we've seen is very useful. It allows us to represent the joint distribution as a product of different terms. Well, the chain rule, even without conditional independence, allows that. But the conditional independence allows us to simplify many of those terms in the factored form of the joint distribution. And all of these different approaches to graphical models are really an attempt to make it easy for an algorithm to take advantage of assumptions about which variables are interdependent versus conditionally independent of one another. And all three of these notations, factor graphs, undirected models, and directed Bayes nets that we've talked about, are attempts to come up with notations that make it easy to develop algorithms that take advantage of the potential to factor that joint into subcomponents. So I think that's all I want to say about Bayes nets. We'll come back to it from time to time, but next time we're going to start off on a different topic. So catch you then.